All right, we're going to start at 5:03, which is in about another minute. All right, looks like a lot of people have showed up. Thanks everybody for coming today. Today we're going to be talking about polynomials. So that's an important concept in algebra. Um, Before that, so how's everybody doing? Did people take the AMC 10 or math counts or anything like that? Because we talked about math counts chapter last time for the talk. Um, did how did math counts chapter go for everybody?
You guys hear him? Or
Yeah,
We can hear.
yeah, we
can
can
someone
hear.
hear me?
I think
All
it's
right,
I think it's on your end.
We can hear.
all right. You can put this in the to everyone chat, by the way, just the chapter and AMC and all that for when we're asking for answers for examples and stuff, then you can then please just send it to one of us. But so how was chapter? MC chapter was very fun. Nice. So it was all online this year. We hope that the chat was not open for everyone. That's fine. Yeah, we hope the strategy session we did a week ago. We hope that helped you guys prepare a bit or test take um anything like that. So yeah, we hope math counts chapter went well. AMC 10 was also this week. I don't know if many of you took that, but that was also all online. So yeah, many of the things we are teaching um throughout Pacific Math applied to a lot of math counts as well as a bit of AMC 10. As some people have pointed out, the stuff we're teaching in Pacific Math, the sort of general level, is more geared towards math counts and early AMC 10 or mid AMC 10. The variation difficulty of AMC 10, excuse me, it varies, but in general, we're going for a bit of a sort of math counts in AMC 10 sort of leveled questions instead of AMY or beyond that, because then it starts to get really hard and we want to benefit the most number of people possible. So today's topic, which is polynomials, appears a lot in math counts as well, specifically quadratics and linear equations, but we'll get into all that. So yeah, we hope you are benefiting from these classes and yeah, let's get started. So Nivid, you want to start? And from now on, please, for the chats, just send it to one of the co-hosts, which is myself, Nivid, Alan, or Suyash.
Can you make me a co-host? Sorry, I'm not a co-host
Right.
yet.
Yeah. Let me do that. But yeah, from now on, just please message only one of the four of us instead of everyone. But today, me and Nivid will be teaching, and let's get started.
All right, so today we're going to be going over polynomials, which are a really important aspect of math, and they're also a really broad aspect of math. So we're going to be going over polynomials this week and next week, and this week we'll kind of go over like the basic fundamentals of polynomials, and then next week we'll move into a little more like harder stuff. So introduction. A polynomial is a specific kind of function that is fundamental to many concepts of algebra. A polynomial is a sum of multiple exponents of a variable. Let's, for example, say x, because x is one of the most common variables we use. So it's the sum of a bunch of different terms, and each term is made up of a constant times a variable like x to the power of some other constant or variable. So here's a formal definition. In general, polynomials are expressions of the following form. So p of x equals an to the an times x to the n plus an minus 1 times x to the power of n minus 1 all the way to a1x plus a0. And this is true for some coefficients an all the way through a0. And this just means like some number. So for example, an could be 5, could be 6, could be any um, number, could be any uh, real number or imaginary number, just any number. So for example, p of x equals x cubed plus 7 has a degree 3. So degree which we call degrees of polynomials the highest exponent of x. So for example, p of x equals x cubed plus 7 has a degree of 3, and this just means that the highest x term, or you could say that like biggest power of x is 3. So other examples of polynomials using the variable x are 2x plus 3, and here the degree is 1, and minus 3x plus 7, here the degree is also 1, minus 3x squared plus 7x plus 13, here the degree is 2, and then x cubed plus 7x squared plus 2x plus 9, and here the degree is 3. So if you notice something, polynomials can have any number of terms and um, any number of like x powers of x, you could say. But one thing to note is normally when we write polynomials, we combine like terms. So if you notice, there's only one term that has x. There's only one term that has x squared. There's only one term that has x cubed, and so on. All right. Um, Another thing which we kind of didn't include here, but there's another term called the leading coefficient. And the leading coefficient is the coefficient in front of the highest power of x. So basically you can think of an as a leading coefficient. So here the leading coefficient would be 2. Here the next example, the leading coefficient is negative 3. The next one, the leading coefficient is negative 3 again. And the last one, the leading coefficient is 1. All right. So the next concept we're going to go over is roots. So an important property of polynomials is that we often study is called their roots. So a root of a polynomial, p of x, is a value r such that p of r equals 0. So this is saying if we plug in r for the variable, like in this example x, then the result would be 0. For example, there's only one root of the polynomial p of x equals minus 2x plus 3, and that is 3 halves. And this is because if we plug in 3 halves for x, then we get minus 2 times 3 over 2 plus 3, and this equals 0. And we know this is the only one because we can try solving it, and I suggest you everybody try solving this on their own by replacing p of x by 0, so saying 0 is equal to minus 2x plus 3, and then solving for x. And if you solve for x, you should get x is equal to 3 over 2, and this means that the root and the only root of this function is 3 over 2. So like I said, we can find the root by setting p of x equal to 0. So for example, in this specific example, we say minus 2x plus 3 equals 0, and then we can solve for x and find the root. The roots of a polynomial p of x equals x squared plus 5x plus 6 are negative 2 and negative 3. Since p of x can be factored as p of x equals x plus 2 times x plus 3. And factoring just means kind of splitting it apart into these kind of things where the degree is into like two, you could say binomials or two polynomials where the degree is 1. Or factoring just means kind of taking out terms that you can take out. So for example, if you look at the factored form here, it's a little simpler to look at than this form here, and we can find more from here. So looking at this, we want, as we said earlier, in order to find the root, um, of this equation, we can set p of x equal to 0. And in order for this equation here to be 0, either x plus 2 equals 0, and then it doesn't matter what x plus 3 is, or if x plus 3 equals 0, then it doesn't matter what x plus 2 is, and that's how we can find the root. So we can say that x plus 2 equals 0 or x plus 3 equals 0, and thus we get that x equals negative 2 and x equals negative 3 are both roots. So another way of thinking about this, um, kind of more on a abstract level, is like if you have a graph. A lot of people, I think, would have seen graphs of polynomials. Then it crosses the y-intercept, the x-intercept twice, and these are the roots of the polynomial. Just because in y is equal to 0, and y is another way of saying p of x. So in general, when we are trying to find the roots of a polynomial, it's often useful to try and factor the polynomial. So just take out as many like terms as we can. So here's a theorem. We can
I think you're frozen.
Yeah, I
think he
think Nivid
froze.
froze.
1
Yeah.
times x minus r2 all the way to
He's cutting in and
So
out.
Nivid, you're freezing. Can you mute yourself and maybe I'll cover this part just so that we can make sure it's smooth. Here, I'll start screen sharing.
kind of important to note here in a way um, is that uh, okay, sorry. So
Wait, Nivid, can you start over from the theorem because you were cutting out after that?
all right. So the theorem for this is kind of p of x equals x minus r1 times x minus r2 all the way to x minus rn for some r1 through rn. Then the roots of p of x are simply r1 through rn. And the most important thing to note about this is that it's x minus r1 and x minus r2, and the roots are positive. And if you think about this, it's because the roots are when p of x equals 0. So if any of these binomials are equal to 0, then that means that p of x would be equal to 0 because 0 multiplied by anything is 0. So x must be equal to r1 in order for x minus r1 to be equal to 0. And the same is true for each of these binomials, and thus the roots are kind of the opposite of this. So this is like minus r1, and then this is positive r1. And not only this, but we'll get into this a little bit more later, but the number of roots, you can say, is the same as the degree of the polynomial. So we'll get more into this later, but that's just something to keep in mind for now. So this makes sense because we immediately have that p of r1 equals 0, since the factor r1 minus r1 equals 0, and then the whole product here is 0 times something, and 0 times anything, as we know, is 0. So similarly, we can say the same thing with p of r2 and all the way till p of rn. And to decompose p of x as the product of such factors as shown above, we need to factor p of x. And that is why factoring polynomials is important. It helps us find the roots, and we'll see in like more examples down the road that roots are really helpful to do a lot of things with polynomials.
All right. Can you guys see my screen? All right. Yeah, so what Nivid was saying was how we can find the roots of a polynomial given the coefficients or given the polynomial. It's important to be able to find the roots by factoring it. So that was a little fast, the way we covered why this theorem holds and how if we factor it, then why are the roots r1 through rn? Intuitively, why does that make sense? What even is factoring? How can we relate that to the way we usually know polynomials, which is in terms of their coefficients? So there's an very important concept, which is relating the roots and coefficients of polynomials. So this will also sort of serve as a review if you're sort of confused by how we covered roots in the previous slide. So the following is something that is not emphasized explicitly often when polynomials are taught, the relation between roots and coefficients. So what's the way we usually learn polynomials? Well, like we did it above, we said a polynomial is defined as a sub n times x to the n plus a sub n minus 1 times x to the n minus 1 and so on. And that's just notation. All that means is, for example, we can say a polynomial is like 2x squared plus 3x plus 7. Now, what's the key in the way we're describing that? We're basically saying here are the coefficients of the polynomial. So remember, the coefficient of x squared in a polynomial is the number of times that x squared appears. So it's the number that appears before x squared in the expansion of the polynomial. So the way we usually are we usually are given polynomials is by their coefficients. But there are two ways to describe a polynomial, which is by its roots or by its coefficients. So let's just recap of the coefficients method. The first way you are usually taught is by coefficients, like we did. We said a polynomial is defined to be some a sub n, which is some number times x to the n, plus something times x to the n minus 1, plus blah, 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 plus something times x plus something, all right? So this is describing the polynomial by its coefficients, a0, a1, a2, a3, all the way till an. That's describing, say, a quadratic polynomial. A quadratic is just a polynomial with degree 2. So that's like describing a quadratic by its coefficients, like 2x squared plus 3x plus 7. But there's actually a very important other way to express polynomials and with factoring. So another way to describe a polynomial in general is by its roots. Is the fact that given a polynomial of degree n, a polynomial of degree n has n roots. So we can describe a polynomial if we are given its roots r1 through rn. So this is sort of a fundamental way to think about how we can even describe a polynomial. If I give you the set of coefficients, if I say the coefficient of x squared is 2, the coefficient of x squared is 1, and the coefficient of x to 0, which is the constant, is 3, then the polynomial would be 2x squared plus 1 times x plus 3. So if I give you the set of coefficients, which is just a set of absolute numbers, then you can then you can tell me what the polynomial is. But what I'm saying here is that there's another way to describe polynomials, which does not rely on the coefficients. Let's say I tell you that the roots are 2, 1, and 3. Then the polynomial would be x minus 2 times x minus 1 times x minus 3. Now, the reason this makes sense is that in order for 2 to be a root of a polynomial, we must have x minus 2 in its factorization, so that when we plug in x equals 2, that sort of cancels out and we get a 0. So if I tell you the set of coefficients, then the key point is this. If I give you a set of numbers, then that can be the coefficients of a polynomial. That's one way to describe it. But another way to describe a polynomial is by the set of its roots. All right. So let's say I give you some numbers r1, r2, r3, all the way till r sub n, and I tell you these are the roots of p of x. Tell me what p of x is. Describe p of x. Then the polynomial is x minus r1 times x minus r2 all the way till x minus rn. Now, so far you might have just been seeing these sort of similar looking expressions floating around, some sort of x minus r1 binomial, x minus r2, but this is the very fundamental way to think about all these concepts. So this slide sort of glues all the concepts we've already talked about together. Given the coefficients, we can describe the polynomial, and given the coefficients, we describe it by simply putting those numbers in front of each of the exponents of x. So that's one way to describe a polynomial. And given the roots, then the polynomial is x minus r1 times x minus r2 all the way till x minus rn. In fact, we can multiply this entire expression by a constant. So for example, c times x minus r1 times x minus r2, blah, blah, till x minus rn for some c. And the key is that this holds because, remember, a root of p is the number such that if we plug p in, it'll give 0. So r1 is a root because p of r1 is now 0. In this expression that you see, p of r1 is indeed 0 because p of r1 would be r1 minus r1 times r1 minus r2 times blah, 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 but r1 minus r1 is 0. So the key point is that if I give you a set of numbers, you can describe, and I tell you these are the roots of p of x, then you can describe p of x using this expression. All right, so that's that. Now, we've described two ways to give a polynomial, which is by its roots or its coefficients. But a natural question arises, which is there any way to relate these? After all, there's only polynomials are a fixed sort of group of things. Can we relate the roots and coefficients of a polynomial in some way? So in general, it is difficult to find the coefficients of a polynomial if you are only given the roots. And vice versa, it is also difficult to find the roots of a polynomial only given the coefficients. So this is kind of a mouthful. Let's break this down. Let's look at the second part first of this sentence. It is difficult to find the roots of a polynomial. Oh,
You keep freezing
can you
like
guys hear me?
every
Nivid, can you hear me? Oh,
You keep freezing every time.
Is this better right now?
We can hear you right now, but you were cutting out earlier.
Okay. Can you hear me now? Am I breaking up?
No, you're good now.
Okay. Yeah, I'll just try it again. So what I was saying is that is there a way to relate the roots? And by the way, if I freeze up anytime, Alan or Nivid or Suyash, one of you guys just tell me when I start freezing up. All right. All right. So what I was saying is that is there a way to relate the roots and coefficients of polynomial? Let's say I give you a polynomial in terms of its coefficients. So for example, let's say I tell you the polynomial is 2x squared plus 3x plus 7. Can you find its roots? Now that involves factoring, like Nivid was saying. So given the coefficients, the only way to find the roots is by factoring the polynomial. So like we did in the example before, we had x squared plus 5x plus 6. So we're given the coefficients. We're given that the coefficients are 5, and 6. And there we had to factor it. So this might be a concept unfamiliar to some of you, but we'll get into more of that. So given the coefficients, if to find the roots, you need to factor the polynomial. And given the let's say you're given the roots of the polynomial, how do you find the coefficients? That's by expanding. So let's say I tell you that the roots are 2 and 3, then the polynomial would be x minus 2 times x minus 3. Now, how do you find the coefficients? You have to expand that. So expansion is something that you all have learned in algebra. How do you expand products of expressions? So given the roots, you can write it in this form, x minus r1 times x minus r2 and so on. And then you can find the coefficients by expanding this. That's the method to find the coefficients given the roots. And to find the roots given the coefficients, you need to factor the polynomial. So just keep these concepts in mind. They're not super important to memorize or anything, but just keep in mind that to find the roots, you need to factor, and to find the coefficients, you need to expand. And an important thing is Vietta's formulas. So next week, we're going to talk about Vietta's formulas, which is a very key concept which also relates the roots and coefficients of a polynomial. In particular, we're not going to go into the details this week. We're going to cover more of those next week. But Vietta's formulas are a set of equations that allow us to find relationships between the roots of a polynomial given the coefficients. So in general, this entire slide about factoring, expanding, this x minus r1, x minus r2 product, it's all relating the roots and coefficients of a polynomial. So that's the main takeaway from this concept, which is that to represent a polynomial, we can either represent it by its roots or by its coefficients. And those are both valid ways to talk about polynomials. So now let's do an example which relates a lot of these concepts. Now, like we said, I don't know if we mentioned this explicitly enough, but these classes are going to be very hands-on. So we're going to be doing a lot of examples, and you should definitely have a piece of paper and a utensil of writing to, work through these examples. So if you don't have that, then try and get that right now. This problem is from the Harvard MIT Math Tournament, HMMT, and take a few minutes to try it. It's going to be on the screen, and then we'll go through how to solve it. Again, if you don't have a piece of paper or a pen or anything like that, please make sure you have one. We're going to be doing tons of examples in future classes and in today's class. So take a few minutes and try and attack this problem relating the coefficients and roots of a polynomial. We're going to come back at around 5:30, which is in around 4 minutes. So take your time. And yeah, if you have any questions or if you want to confirm your answer, message one of the staff, which is me or Nivid or Alan or Suyash. But yeah, make sure you don't message everyone. Somebody's asking about the handout. That's going to be uploaded after the class. We couldn't get it out by this week, but that'll definitely be uploaded after today's class. Somebody's asking about what P of 1 means. P of 1 just means what happens when we plug in x equals 1. So a polynomial, when we plug in x equals 1, uh, we can find a value if we plug in a specific value of x. So P of 1 is just the value we get from the polynomial when you plug in 1. We're going to take about another minute, and then we'll go through the example.
All right, now we are going to start working through it. Um, if you're still working on it, go ahead and keep working on it, or you could look up if you need help. So first, what we want to do is when we look at this problem, there's a lot of information, but we have to see that, okay, the problem gives us a bunch of different things. There's one thing in particular which is going to help us. So we look at it, the first part is pretty simple. It just says p of x equals x cubed plus x squared minus r squared x minus 2020. This doesn't really help us right now. I mean, obviously it's the main part of the problem, but this doesn't help us solve the problem. The next part says be a polynomial with roots r, s, and t. So this is pretty straightforward. It has to have 3 roots because it's to the power of 3 and its degree is 3. But the important thing to note is that the only important root that we care about is r, because we see here that it says minus r squared x. So that's the only root we care about. S and t can be anything, and we don't care about them. These are just what we call fluff, meaning they're things that are kind of important to the problem, but they're not important to the solution or how we solve it. So keeping this in mind, we can start to solve it. So there's a really bashy way to solve this, which just means we can kind of like just like bash it out, just try to factor it, try to do something and figure out the answer. But there's a slick way, which is based on relating the coefficients like we talked about earlier and the roots. So the key here is to note that we are given r as a root of p of x, and r also appears inside of p of x. So it appears in the third term. So we know that p of r must equal 0 because that's what the definition of a root is, that when you plug in r for x, then it equals 0. And since we know this, we can plug it in and get this. 0 equals p of r equals r cubed plus r squared minus r squared times r minus 2020. And then if you notice here, the first and third term cancel out because it's r cubed minus r cubed. So then we are left with r squared minus 2020. So using this, we can kind of, since we know 0 is equal to r squared minus 2020, we can move the 2020 to the other side and we get r is equal to the square root of 2020. So this is pretty simple right now. And then now since we know what r is equal to, we can easily find p of 1. So we have p of, um, we also have, so we can, um, okay, sorry, I also should say something else. So here we kind of left this by saying that r equals the square root of 2020, but more precisely, it could be positive or negative square root of 2020. Because as we know, let's say we take the square root of 25. This could be positive or negative 5 just because 5 times 5 equals 25, and also negative 5 times negative 5 equals 25. So thus we can, it's r doesn't equal the square root of 20, it equals plus minus the square root of 20. Either way, however, we have the original polynomial, which is p of 1 equals our p of x equals x cubed plus x squared minus r squared x minus 2020. And if we plug in 1 for x, we just have 1 plus 1 minus r squared times 1 minus 2020. So this equals 1 plus 1, and r is equal to plus minus 2020. But because it's r squared, it doesn't matter. It becomes positive anyway. And we have r squared here as 2020, so we already know that. So we plug in 2020 for r squared, and thus we get 1 plus 1 minus 2020 minus 2020, and this gives us negative 4038. So the key here is to realize that since r is a root, we know that p of r equals 0, so we can plug it in and solve. And um, once again, looking at the problem, it might not be too obvious to look at this, but we just had to look at this and say that this line right here is kind of redundant because you know there's going to be 3 roots. But the important thing to note is that we have r here and we have r here. And since it's the same, even if we don't know too much and we don't know how to solve the problem, we can just try doing the one thing we know how to do, which is plug in a root for x, and then we can get that that's equal to 0, and then that can help us. So even if we don't know that's eventually going to help us, we can easily just try it and see what happens. And most likely it will help us if this is the information they give us.
Does anybody have
All
any
right.
questions about that? Let's maybe stop for a minute. If anybody wants to read through the entire thing or has any questions about that, you can message us in the chat. We'll just stop for about a minute. All right, I'm not getting any questions in the chat. Unless you guys are, I guess we can move on. So now we're going to be going to a slightly different topic, which Nived's going to go through.
All right. So the next thing we're going to go over is linear equations. So before we dive into general polynomials and all the random terms of x, it's important to first study linear equations to build some intuition, because linear equations are the most basic type of polynomial. It's just ax plus b, it's just x to the power of 1. In most polynomials, our goal is to break them down into a bunch of different linear equations in kind of a abstract sense, you could say. So definition: a linear expression in x is a polynomial in x with a degree 1. So the general linear expression for x is ax plus b for some constants a and b. So this is pretty simple. A linear equation, most people recognize this as a line on a graph. Any perfectly straight line on a graph is a linear equation. So if like y equals x, that's just a diagonal graph. X equals 5, that's just a straight line on a graph. These are all examples of linear equations. So it is an important fact that linear equations have exactly one root, and sometimes they will have no roots. For example, if our first example, x equals y, this has one root, which is 0. And our second example, x equals 5, this has 0 roots because y or p of x is never going to be equal to 0 because it's always going to be equal to 5. Oops, I meant y is equal to 5. Sorry, I misspoke there. But
Oh,
if we take a linear
wait,
equation, y is equal to 5, then there's never going to be any roots.
yeah. So Nivid, when you say y, you just mean p of x, right? Or like
Yeah.
the
So
linear expression.
yeah.
Yeah, got it.
So by y or p of x, I just mean what the total expression evaluates to. So for example, if a is equal to 0, then p of x or y is always going to be equal to b. And if b is not equal to 0, then it will never have any roots. And similarly, it could have an infinite number of roots if it's just p of x or y is equal to 0. But we're not going to worry about that too much because that's a really specific case, and that those kind of cases are rare and they're really self-explanatory. So in every linear equation, it's either going to have exactly one root or sometimes no roots. So note that if we multiply a linear expression in x by a constant, the new expression will still be linear. So if we take this expression here and multiply everything by c, some other constant, it'll be acx plus bc, which is still linear. So for example, 2x plus 3 is linear, and if we multiply 5 by 2x plus 3, it becomes 10x plus 15, which is still a linear equation. So also adding and subtracting constants from linear expressions keeps them linear. So taking the same example, 2x plus 3, if we add 7 halves, it becomes 2x plus 13 over 2, and this is still a linear equation. So this also holds with most general polynomials. Multiplying a polynomial of degree n by a constant keeps it the degree n, and adding a constant also keeps it a degree n. So just a quick review about linear expressions. The general form is ax plus b, where a and b are constants, and they will always have one root or no roots. And if we multiply them by a constant or multiply any polynomial by a constant number, then the degree will stay the same. And if we add or subtract any constant from any polynomial, then the degree will also stay the same. So next, we're going to move into a linear example problem. And this one is a little bit tricky, but it shows some intuition about linear equations. So let f of x equal 15x minus 2016. If f of f of f of f of f of x equals f of x, find the sum of all possible values of x. So take a few minutes to try it. Again, this one's a little bit hard to kind of break into and get into, but just try to understand the problem and try to figure out a basic way of attacking it. And in a few minutes, we will start going over the solution. All right, just a few more minutes for everybody to get a chance to work on this problem, and then we'll go over the solution.
All right, so we'll come back at 5:45, which is in 3 more minutes. So take your time. All right, let's get started on the walkthrough. So this one is a bit of a tricky problem if you haven't seen this kind of thing before. Well, it's not like if you haven't seen it before, then it's hard, but this problem does go over a lot of concepts. It explains a lot of concepts that relate to linear equations, and so let's get into it. So if you were trying this problem, one thing you might have started is trying to expand this massive f iterated by itself 5 times. Iterated just means if we iterate f onto itself twice, that just means f of x. So here f is iterated 5 times. And one thing you might have been trying is how do I even start iterating f so many times? The expression is probably going to be really nasty. How do I deal with this? So that's sort of what I was saying when I said that's sort of an initial roadblock that would hinder subsequent progress. So it looks very intimidating at first sight. How are we going to deal with iterating f so many times onto itself? And especially since f has such big numbers like 2016 in it. So when you iterate many times, those numbers are just going to get bigger. So how do we do this? A general strategy here is to simplify the problem and then try to solve it. So the main roadblock here is that f is iterated onto itself 5 times in the LHS. LHS just means the left-hand side. So let's try to write down what happens when f is iterated once, twice, thrice before jumping to 5 times, and see if anything interesting pops up. So remember, we're trying to solve the equation f of f of f of f of f of f of x. So that's 5 times. F to the 5th of x, that just means iterated 5 times, is f of x. And we're trying to find the sum of all the solutions to that equation. So if we iterate f once, it's just 15x minus 2016. That's just f. If we iterate it twice, it's 15 times. So remember, f of x would be 15 f of x minus 2016 because f of x is now the input. And f of x is 15x minus 2016. So f of x is 15 times 15x minus 2016 minus 2016. Now f cubed of x, f to the 3 of x just becomes worse. It's this expression over here. I'm not even going to read it out loud. But so the point is that these equations are getting really nasty. How do we deal with any of this? So this is getting ugly fast. Now here's the key point to the solution. All of the above expressions are linear in x. Let's go back. So f of x is 15x minus 2016. That's obviously linear. The next expression is f of x, which is 15 times 15x minus 2016 minus 2016. Now remember we said above that if you take a polynomial and you multiply it by a constant, the result is still a polynomial, and in fact it has the same degree. So in particular, 15 times 15x minus 2016 is also linear. Now, if you've ever heard of the concept of slope, the slope of a linear equation is for example, here it's 15. It's basically the coefficient in front of x. You might have heard of y equals mx plus b as the general equation of a line with slope m. So here the slope is 15. In this case, the expression is still a linear expression, and it has slope 15 squared. Now that's not necessary to the solution, but the point is that these, when you iterate f over and over, the expression stays linear. That's the key point. Here it's 15 squared x minus some constant. If you expand this out, that's a linear function in x. So all the above expressions are linear in x. So in particular, because multiplying a linear function by 15 and subtracting by 2016 keeps it linear. Here we were multiplying by 15. We took this linear expression, multiplied it by 15, and then subtracted 2016. So that keeps the fact that it's linear. At each step, iterating f does not change the fact that it's linear. So in particular, f to the 5th of x, which is f iterated onto itself 5 times of x, that is also linear. So this expression right up here, remember, we're trying to solve the equation f to the 5th of x equals f of x. So f to the 5th of x is linear. That's what we've concluded. So f to the 5th of x is linear. Also, f of x is linear. So their difference is also linear, because if you have a linear function and you subtract another linear function, the result is linear. So we are trying to solve the equation, recall, f to the fifth of x minus f of x is 0. That's just an equivalent way to write f to the fifth of x is f of x. And we now know that this right here is a linear expression from our deductions above. So at the end, what we're trying to solve is a linear equation equals 0, which has at most one solution. So at most one value of x works. Now here's the key point. The problem was sort of a troll because it asks us find the sum of all possible values of x. So that sort of keeps us from guessing that there's exactly one value of x that works. The key is to realize that this is linear and this is linear. So their difference is linear, which means that there's going to be at most one value of x that works. So the sum of all possible values of x, that's just asking for the one possible value of x that works. So now we need to find, so all of this just tells us that there's at most one value of x which works. It doesn't help us find any value of x so far. It just tells us that there's a linear equation, so it has at most one solution. So now we turn to finding an quote unquote obvious value of x which works, because if we can find a single value of x which works, then we know it's the only solution. So suppose f of x equals x. Let's go back up here. Remember, f of x is 15x minus 2016. So if f of x equals x, there certainly exists such an x that satisfies that. Then if f of x equals x, then f of x is x, f of x is x. I'm not going to try and say that more. But the point is that since f of x outputs itself, any number of times you iterate that, it's not going to change. So in particular, if f of x equals x, then clearly both sides of these are the same. So that gives us one value of x that works if we can solve that equation, and therefore we know it's the only value of x. The logic here is a bit complicated if you're having trouble following. So try and go through the recording after, or the handout which we'll upload after class, to follow through all the logic and see how we were able to deduce that there's only one value. So we turn to finding an obvious value of x which works. If f of x equals x, then all these iterations just boil down to x. So if we solve for the value of x which satisfies f of x equals x, then we know that value of x is the only solution. Now we can just solve. So f of x equals x implies 15x minus 2016 is x. Move the x to the other side, you get 14x is 2016. Dividing by 14, this implies x is 144. So we know that x equals 144 is a fixed point of f, which just means that when you plug it into f, it outputs the same value, which means that it's the only value of x which works, which means the sum of all possible values is there's just one value, which is 144. So let me just summarize this solution again. The key is that we have 15x minus 2016 and we're iterating it over and over. And that keeps the fact that it's linear. So this is linear in x and this is linear in x. Another way to think about it is that these are two lines in the coordinate plane because they're both linear equations. And two lines, if you can think, they only intersect at one point. Two lines can only intersect at one point, or 0 if they're parallel. This is a geometric way to think about it. But in this case, they're not parallel since the slopes are different. So they intersect at a point, and that is the exact, which means that there's exactly one solution to this equation. And solving it just requires to guess that f of x equals x, and then both sides are clearly equal. So that this example really highlighted a lot of concepts about linear equations. The fact that, their graphs are lines, for example, that's a geometric way to think about it. And that, there's exactly one root to any linear equation, which allows us to deduce that there's exactly one solution. From there, it's obvious. So yeah, this example really highlights a lot of key concepts about linear equations. Now go through this example if you're still confused. We're going to go through one more concept, which is about quadratic equations, and then we'll wrap up. And we'll get into more polynomial stuff next week. So Nivid, you want to get into that?
All right, here we go. All right, so quadratic equations. Quadratic equations are just as important as linear equations, especially because they're really common in math. A lot of things can be broken down into quadratic equations. So we have a quadratic polynomial, and this is the general form for a quadratic polynomial. P of x equals ax squared plus bx plus c. So a, b, and c are all constants and coefficients of the terms, and then we have x squared, x, and x to 0, which are all the x powers, and so on. So what we want to do is we want to find the roots of this. And obviously the most ideal way to find the roots would be to factor it, but not all polynomials are factorable, and often sometimes if you want to factor it, the factoration becomes like really messy. Sometimes there's no option but to kind of go a different way and not factor it. But ideally, if you can easily see that it can be factorable, like maybe it's something really simple and you've seen it before, or some way that you can easily see it's factorable, then you want to factor it. But if you haven't seen it before and you try factoring it, but it's near impossible, and it's just too much work to factor it, then we use the quadratic formula. So the quadratic formula is a formula as it's in its name that tells us what the roots are. So it tells us for what values of x, ax squared plus bx plus c is equal to 0. So the roots are negative b plus minus the square root of b squared minus 4ac all over 2a. And the plus minus means that the square root can be either positive or negative. And this is really key here because, well, if you notice this, it's a quadratic, which means it has two roots. And by having the plus minus here, it will always have two roots. One root will be minus b plus square root of b squared minus 4ac all over 2a. And the other one will be minus b minus the square root of b squared minus 4ac all over 2a. But there's one case where it will either have 0 or no roots, or 1 or no roots, sorry. And this is based on this thing right here. Um, I'll get back to that in a second. So hence the expression above shows two values, and we will not go through the proof of this formula, but it's very important to remember. So before we move on, I want to point out that this kind of square root thing here is what we call the discriminant. And this is really important because this tells us how many roots there could be. In most scenarios, there will be two roots, but sometimes there could be one root. So let's say that b squared minus 4c is equal to 0. Then it would be minus b plus minus 0, and plus minus 0 is the same thing. So there's only going to be one root, which is minus b all over 2a. And there's only one root if we have something like something as simple as x squared. There's only one root with with p of x equals x squared, and that root is 0. And on anything where we have where we only have one root, it'll be because the discriminant is equal to 0. On the other hand, we could have 0 real roots. And I point out by saying real because there will be imaginary roots, but let's say that 4ac is bigger than b squared. Let's say b is 1 and a is 1 and c is 1. Then it becomes 1 minus 4, which is negative 3. And as we know, there's no real number which is the square root of negative 3, and thus on a real graph, there will be no real roots. So, um, so there's not, you don't have to worry too much about imaginary roots right now, but you just have to remember that if b squared minus 4ac is negative, then um, then uh, we do not have any real roots. And if somebody wants to kind of look at the graph of this and see how this will all look on a graph, well, if there's two roots, then the quadratic would intersect the x-axis twice. If there's one root, then it'll just touch the x-axis once. So for example, y equals x squared or p of x equals x squared. If you graph it, then it'll only touch the x-axis once. And then if we have um, imaginary roots, or where 4ac is bigger than b squared, so this is negative, then it won't touch the x-axis at all, and it'll either stay above or below the x-axis. So let's say that R1 and R2 are the two roots of this that we get from this equation. So we get R1 is equal to negative b plus the square root of b squared minus 4ac all over 2a, and R2 is equal to negative b minus the square root of b squared minus 4ac all over 2a. Then we can note that since we know the two roots, we can factor it by saying p of x equals x minus r1 times x minus r2. And this goes back to the idea we had about factoring and when we talked about factoring, because since we know r1 and r2 are the roots, then it's self-explanatory to say that we can factor it simply by saying x minus r1 times x minus r2. And sometimes this will be really neat, like x minus 2 times x minus 3. But other times it'll be really messy because if this isn't a perfect square here, it could have like 1 plus minus the square root of 5 all over 4. And then this becomes messy. So that's why sometimes it's easier to go the way of the quadratic formula rather than trying to like factor it out from the get-go. But there is an example that we have, and we do not have enough time to cover it today, but it's going to be in the handout so you can look at it more on your own.
Yeah, so the handout, like Nivet said, will be uploaded after the class before tomorrow. So look out for that.
And
We will
I
have that
believe the
uploaded.
email may have accidentally said that the handout would be posted before class today. So sorry about any
Yeah,
misunderstanding there.
right. We will have the handout uploaded before tomorrow, and you all will get an email. Sorry for going a couple minutes over, but thank you everybody for attending. And any other announcements, Nivid, you can think of?
Not for me.
All right. Yeah. So class will be next week. We will have the handout uploaded as well as the recording. So feel free if you missed anything to go over those. And yeah, thank you for attending. See you guys next week. Bye.
And just one more thing actually before we go.
Oh,
That next
sure.
week we're going to be going over kind of more polynomial stuff. So if you had any questions or if you were struggling with anything, go ahead and watch the recording again and go ahead and email us if you still have questions. And that way you'll be fully prepared for next week when we go over more polynomial stuff.
Yep. All right.
Okay.
Thank you.
Bye.
Thank you. Bye.
Thank you. Bye.
Bye. Thank you.
Thank you. Bye.
Thank you. Bye.
All right. I'm closing the Zoom meeting now.